All right. Hey everyone, welcome back to Vidyaspace. Let's see, we are going to solve today three sum problem, and this is a continuation to our array playlist, and this will be our second problem today. Okay, so let's try to understand the problem. The problem is saying that we are given with an array of integers, and in this question the target is given as 0, so the target sum is given as 0, but it can be different also. So we will try to solve this problem in a generic way so that we will not be heavily dependent on what is the target 0 or something. We will solve it for any target value. Okay, so the question is asking that we have to find unique triplets which will be summing up to this target value. So if I take an example of this array, if you see this -1, this 0, and this 1 summing up is going to give our target value 0, -1 plus 0 plus 1, right? If I check the other combination, I have one more combination where we will be able to see that if I can take this -1, this 2, and again this -1, so we will be again going to get our target equals to 0 for the sum. Apart from these two unique combinations, there are no any other combinations for this particular array if you see. So by visuals we can easily figure out what will be those combinations and what will be the unique triplets, but how to solve it programmatically. So the very first step will come in our brute force logic, that we will try to run loop on this particular given array and find our indexes which can give up the sum to target. So if I take the same example, I have -1 0 1 2 -1 4. Okay, -4. I will start a for loop with a pointer at the first index, and I can have a second pointer to the second next index to I. Then I can have another third pointer to next to the j index. Okay, and definitely there will be edge cases that we will be having the array elements more than or equals to 3 at least. So we will be having our k pointer here, and we'll start our loop, 3 nested loop. So we will be having first nested loop from for I equals to 0 to n minus 3. Then inside this we will be having again another loop for j equals to 0, which will be running till j equals to I plus 1. Okay, next to the ith index. This will run till n minus 2 position, and inside this again we will have our third for loop for k, which will run from j plus 1 till n minus 1 position, right? Now why we are running these positions till n minus 3, n minus 2, n minus 1? If you think from edge case perspective, when this loop will be going to end, so our indexes should be at max at these situations, right, where your I will be pointing to the third last item, and j will be pointing to the second last, and k will be pointing definitely to the last item, right? And that is what we are doing here with these limitations. We are saying that the I position cannot go beyond n minus 3, and that is what we have here. If I will write my indexes, so this 0th index 1 2 3 4 5, and n is equals to 6. So n minus 2, n minus 3 will be 3, and that is where we will be going at max with our I pointer, because our j is going to be I plus 1, and then k is going to be j plus 1. So that is why we have to limit our I index till n minus 3 only. Okay, and I'm pretty much sure now we can solve this with just a logic here, which will be checking the summation int sum of array of I plus array of j plus array of k. And if this sum is equals target, we can store this combination triplet to our answer. Now there is a unique thing which we have to figure out. We cannot store duplicate items, so we will maintain a set data structure. Okay, and we will be pushing to our set data structure this combination of array of I, array of j, and array of k. Now there will be one more thing we have to think. Suppose my item are -1, 1 and 0, and again I have one more 1, -1, 0. So in this one we can see that the items inside array is definitely the three same items, but the orders are different, and that is where set may figure out that these two are different items. So what we have to do, we have to also do a quick sorting here before moving and adding it to the set. So what we can do, let me just remove it here. Before pushing it to this set, we will create an array, and we will say that we have to make a list. Okay, so new int of size 3 we will have, and we will have these particular items from here, right? These things will be here, and that is where we will be moving our items. Let me write it a little bit cleaner so that it will be more clear. Okay, so here we are saying that whenever the sum is equals to target, then we will be creating an array, temp array, which will be having that three items. Okay, and what are those three items? Those are array of I, array of j, and array of k. Okay, now then we will do set dot add this temp array. This way we will be able to store all the unique combinations to our set data structure, and in the end we can return the set to array. We will convert this set to array, and then we can return it. So this way we will be able to return all the unique triplets. If I talk about time complexity and space complexity of this particular approach, it is not very efficient. This is a complete brute force logic. So here we are running a 3 loop. This can go in the worst case to O of n, again here O of n, and this one also O of n. So these are the 3 nested loops which will boil down to O of n cube. And again here we are doing a sort operation before this particular temp addition to the set. So I think I just missed that part. We will be doing a temp sort. Okay, temp dot sort. This thing is going to actually do take the n log n, right? Sorting takes n log n, but since this is the 3 item at max every time, we will not be having worst case. It is a constant one here, 3 log 3 base 2. So that is why we can ignore this particular one, and set addition takes O of 1. So this way we are boiling down our time complexity to O of n cube, and there is space complexity of only this set data structure and this 3 array of items. So I can say O of 3, which is as good as constant. So this will be the brute force solution for this 3-sum problem. Now, if we talk about the optimal one, definitely we should think little bit better than O of n cube towards O of n square at least, right? So how can we do that? We have to think on it. So here comes the two-pointer approach which we can apply. I'll take the same array example where we were doing the brute force logic, -1 0 1 2 -1 4. Okay, so -1 0 2 -1 -4. Just a sec. Okay, so in this particular array items, we have to do the very first step is do the sorting. Okay, so let me just be with me. I will be giving you the intuition why we are doing the sorting. So if we will do the sorting, we will be having -1 -1 0 1 2, and this -4 will come at the start. Okay, so this will be the sorted array, and we will put our two-pointer logic on this sorted array. So we will start a I position here, and then we have to take one more j position here and one k at the end. So this will be now boiling down to the two-sum problem logic which we are trying to do. If you think this particular section is saying me that we have to find those two particular j and k which with summing up to I can give me the target value. Okay, so we will think in that direction, and that is where we can start our loop. We will run it from the I position to 0, and then we will go for j equals to I plus 1. This will be the one index. I think we can write like this. So j will be I plus 1 and k will be n minus 1 always. Okay, so we have to now run this till the same logic n minus 3 which we were doing in the brute force, and we will move with our j and k position to find this. So let's start dry run. So our target was 0. Okay, now this will be the initial indexes. So I is 0, j is going to be 1, k is going to be n minus 1, which is, if I take 1 2 3 4 5 6, so this is going to be 5. And here what we will do, we will be doing the first step, check sum of I, j, k indexes, and here the sum will give me -4 plus -1 plus 2 is going to give us -5 plus 2 minus 3, which is not equals to 0. So we cannot take this. But if we see, -3 is less than 0, which was our target. So it is saying that the sum is less than target, and that is what we have to remember. In our two-pointer approach, we were doing, if the sum was less than the target, so we have to increase the value of sum, right? So if we have to increase this sum value, we have to move our j pointer to somewhere right side so that we can get some bigger number. Since the array is sorted, that is why we have sorted the array so that we can apply this logic. When the sum is lesser than the target, we will move our j pointer towards right, because we are sure that on the right side of j it will be having some bigger number than the current value of j. Okay, so if we move our j pointer to the next index, this next index is again having the same -1. So there is no need of doing the another comparison. We can simply move to the next position and we can move our j. Let me just clear it out. So we can move our j to 0 position. Okay, we can move from here, again -1, so we'll move to here. So this time the j is now 0. So again we will check the sum. We will be having the sum as let me clear it out here. So we are going to have the sum -4 plus 0 plus 2, which is again -2, and this is also again less than 0. So we need to again move our j index to the next position, and here we will check again. This will be -4 plus 1 2. So -4 plus 1 plus 2, which is -1, right? And it is also less than 0. So our j will now, if move, we will be moving towards equals to k. So at this position j will be equals to k. Then our condition will not satisfy. We want 3 unique positions, so we can move j only till if it is less than k. So we will be having a while condition where j can only go one step back to k, and we will check if sum is equals to target, then we are going to do the answer. I'll just keep it here for now. But if the sum is less than target, we have to definitely move our j index, and we have to also be sure that whenever we are moving, we will make sure our j is less than k because of this condition. Okay, so there can be another condition when the sum will be greater, so we will do the opposite. When the sum is greater, we are going to do k minus minus. We will move our k position to the back side. So let's continue. Since we are done with this one, so now this for loop will move from I equals to 0 to next position. So we will again reset our position. So our new positions will be the I equals to 1. Now our position I is here, j will be here, and k will be as usual last index. Again we will do the comparison check. So we will do a check here that -1 plus -1 plus 2. Wow, this is giving me sum equals to 0, which is our target. So if for any I, j, k pair triplets, if we are getting sum equals to target, we have to do simply set dot add that 3 temp array, right? And that temp will be nothing but, this temp will be array of I, array of j, array of k. And this time we don't have to do the sorting because this array is already sorted before this operation started. So we are pretty much sure that this combination will always be a unique combination. So set is going to store that combination here. Okay, now if I move to again next, since this ijk is done, what we will do, we will be moving our j position to the next index. Okay, I'll take this j and move to the 0th position and then again check. Are we able to get it? If we will be able to get it, so minus 1 0 2, no, we cannot get it. So the summation is minus 1 0 and 2 is giving me sum equals to 1, which is now greater than our 0 target. So this time we have to move our k position to backward because we have to reduce our sum value. The sum is greater than target. If sum is greater than target, we have to reduce it. For that, we have to move our k to the left side. Now we will again check. So this time the summation will be minus 1 0 1 and we got another 0 equals to target, right? So again this logic will be applied, set dot add temp, and we will be having our data structure where we are storing this. So we will be having two arrays now. One will be the minus 1 2 and the another will be minus 1 0 1, right? Then we will move back again. Since now j and k cannot cross each other, our while loop will end and we will again move with our I position to the next index, and then we will again reset our ijk. So this will continue. Our I will come here and this time this j will be here and this k will be going to be n at the end again, right? So this will be the new reset position. If we will do again check, so we are going to get again minus 1 0 2. This is going to give me minus 1 0 2 is going to give me 1. So this time again the sum is higher. We have to see this will give me the same combination minus 1 0 1, right? If I will move it here, so our ijk is again going to give me minus 1 0 1, which is a pair we have already stored here. So this is a duplicate pair and we have unnecessarily done this comparison here and done this loop, right? Because if we see here, the reason was very much straightforward. Whenever our I value was minus 1, we had done a combination in this range. Now again we moved our I value to this next index, which is also the same whatever it was previous. So the new range is this much, which was already computed with the same value in a bigger range, right? So if there would have been any answer, we would have already covered it. That is why we will skip if my next I index is having the same value which is my current one. So we will add a quick check here in our for loop start, that if my I is greater than 0 and an array of I plus 1 is equals to array of I, we will be just continuing. We don't have to restart a j and k position because we have already done this jk combination with that value in our previous iteration. Okay, so this way we will be able to solve this question. Now coming to the time complexity and space complexity. So if we see here, we are using a for loop which can go in worst case to O of n, right? Now we are using one more thing, which is a while loop, and this while loop is running in the range of this much, right? So from I plus 1 to n minus 1. So this is the range of this while loop where we are checking at max all the elements. So this can go also in worst case to O of n. Okay, so this is inside nested for is inside this for loop. So this is the nested one. So we are doing O of n, and inside it again we are doing a for loop which will go, while loop which will go to O of n. Okay, so this will boil down to O of n square. And before this operation start, we have done a sorting. So sorting will also take n log n time complexity. So we are doing n square plus O of n log n time complexity. Okay, and that is where the time complexity will be. So space complexity wise, we are, if you see, we are only storing the data. We are nowhere having anything where we are doing any operation. We just have that temporary array to store the answer, and this is getting added to the set. We are not running any logic over here. So space complexity would be O of 1, which is constant. Okay, so I think this is it for today. Thank you.